Hello again, how are you? Let's talk about derivatives and their relationship with whether the original function is increasing or decreasing or constant. If a is less than b, real numbers of course, and if f is a function on the open interval ab into the reals such that real number a less than real number x less than real number y less than real number b implies that f of x is less than or equal to f of y, then f is said to be increasing on AB. And if we replace less than or equal to with less than, then f is going to be said to be strictly increasing on the open interval AB. And guys, when we do increase and decrease and constant, we're going to be doing this on open intervals, non-empty ones at that. Okay. So anyway, and again, non-empty. We don't want empty. Okay. If a is less than b and if f is a function on the open interval ab into r such that, again, a less than x less than y less than b implies f of x is greater than or equal to f of y, then f is said to be increasing on ab. No, I need to fix that, don't I? Sorry, that's decreasing. My bad. Oops. So I'll save that in the editing. Nope. Sorry, I need to save that. So let me save this now. And I'll save this in the... Well, I'll save it later, but I'll save this in the editing. So that should say decreasing right here, not increasing. And I do apologize about that, guys. That's my bad. And now that's not necessarily strictly decreasing. We invite the possibility of equality, but notice that if for y strictly greater than x, f of y will be no bigger than f of x. That's what we're saying. Now, in the event that f of y is strictly smaller, then we're strictly decreasing, okay? And that's in a similar fashion as strictly increasing from a minute ago, except now we're strictly decreasing. So let's examine what we're talking about here. So as we're going to the right, our function f is, the graph of f is falling down for strictly for decreasing. Well, for strictly decreasing in particular, it's falling down. For decreasing in general, it's either falling down or flat. Okay. So as we're going right, our graph is either falling down or is flat. Now for increasing, as we're going right, we're either flat or going up for increasing. Okay. So for increasing, we're either going up or flat. For decreasing, we're either going down or we're flat. Now for strictly increasing, we're going purely up as we're going right. Now, I'm talking about going rightward, and so let me back up. As we're increasing, as we're going rightward, we're either going up or we're flat. Strictly increasing, as we're going rightward again, we're purely going upward. Decreasing, as we're going rightward, we're always taking rightward as our direction of choice. As we're going rightward, we're either flat or our graph is either flat or it's going downward. And strictly decreasing, as we're going rightward, we're strictly going downward. Okay. Now, if a is less than b, and if f is a function on the open interval ab into r such that f is differentiable on ab, okay, or just suppose that that is the case for f. So we're letting f be this function that's differentiable on the open interval ab. If f prime is greater than 0, if f prime of x is greater than 0, then f will be increasing at x. This can be proven, but we're not going to prove it. And now if f prime is less than 0, then f is decreasing at x. If f prime of x is equal to 0, now this is f prime of x. This is how f prime is behaving at the particular point x. Okay. If f prime of x equals 0, then we already know that f is constant at x by previous videos, by our comments on the Extrema videos and all that. But anyway, so f will be constant at x. So there's that. So if and again, x is understood to be in the open interval AB, okay? We can't have this conversation if x is not in my open interval AB, all right? But anyway, example, let f be a function in the open interval 0 to infinity to r such that f of x equals x squared. Note that f prime of x equals 2x, which is greater than 0 for all x in 0 to infinity, because if x is in the positives, then 2x would be a positive, so 2x would be greater than 0. So f prime equals 2x would be greater than 0. Hence, because our derivative is positive, by this comment right here, f would be increasing. And in fact, it would be strictly increasing because f prime, hence f is strictly increasing on 0 to infinity. And you know what? Actually, I can strengthen this. If f prime is greater than 0, we are strictly increasing. I can actually be more specific. And in a similar fashion, I can be more specific here. We're strictly decreasing. So sorry about that, guys. I could actually tell you more. I can be more specific. And let me I'm going to save this. Allow me to go ahead and save this in the editing. So sorry about that. Sorry for the interruption there. Okay. So, but anyway, there's that. So hence f is strictly, because without me saying this here, this down here wouldn't necessarily follow. So yeah, for this to follow, I need to let the cat out of the bag right here. Okay. So let me move on down the line down here. Now let f be the function from negative infinity to 0 into r such that f of x equals x squared. Note that f prime of x equals 2x, which is less than 0 for all x in negative infinity to 0. Okay, because now guys, if x is in the negatives, then 2x is going to be a negative number, and 2x, so f prime of x equals 2x would be a negative, and by our comments up here, not by this comment, by a similar comment for decreasing, f is strictly decreasing. This comment right here. By this comment right here, f is strictly decreasing. Okay. So this right here follows from this right here. Okay. So this here is a consequence of this guy right here. Okay. So moving on. Now let f be a function from the reals to the reals. You could just call this r. I'm kind of being silly. Negative infinity to infinity, that is just the reals. I'm kind of being a little bit of a silly person right here. Sorry about that. You could just call this r. Oh well. So let f be a function from r into r itself, such that f of x equals x squared. Then f prime of 0 equals, 2 times, remember f prime of x equals 2x for all x, so f prime of 0 is 2 times 0, which is just 0. Hey, we're constant there. So we know by our comments up here that we're constant there. Okay. Now let f be a function from negative pi quarter to pi quarter into r such that f of x equals sine x. Now f prime is going to equal the cosine of x, and that's going to be strictly positive, strictly, for all x in negative pi quarter to positive pi quarter. Okay, and that's actually really overly strict, to be honest. That's good. I mean, that's fine. If we wanted to push our luck as far as we could push it, we could go on the open interval from negative pi halves to positive pi halves, and this would still be good. That's if we wanted to push our luck as hard as we could push it. If we pushed it any harder than this, we would run out of luck, though. So for, on this interval, f prime is positive, and we are strictly increasing. Now, you can make it more generous, but, you don't have to. You can push your luck a little bit further. Now, let's go down. Let f be a function on the open interval from 0 to pi quarter to r such that f of x equals the cosine of x. Then f prime of x equals the negative sine of x, which is less than 0 for all x in 0 to 4. So we're decreasing. Now, if we wanted to push our luck as far as we could go, we could actually extend all the way from the open interval 0 to pi, and this would still hold true, okay? So f is decreasing on this entire interval here. Whereas on the last example, if I could get back up there, it was increasing on this entire Well, it was increasing on this entire open interval here. Guys, we don't like to talk about increasing on a closed interval. And let me put, so we are increasing. When I say we're increasing, we need to talk about an open interval. And I need to be very, very careful about that. And I'm so sorry about that. I'm profoundly sorry. Let me put the open interval from pi over 4, because our domain is just the closed interval. Because our domain is just this closed interval, we're increasing on the corresponding open interval. And I need to be so careful. We can only say that we're increasing on this open interval right here. I forgot to tell you that. And that's my bad, and I'm so sorry. Your professor would get you for that, and I'm very, very sorry. So we're increasing on this open interval right here. And I'll save that in the editing right now. Okay. Because remember, increase and decrease, it needs to be open interval. Constancy as well. Okay. So we're increasing on this open interval. Now down here, we're in luck. We've already got an open interval, so we're, on this entire open interval, we are decreasing because f prime is negative. Since the sign is positive on this interval, neg 1 times the sign is naturally going to be negative on this interval. So we're decreasing. I'm using what we know from trigonometry. Okay. Anyway. And we could push our luck all the way to pi. I'm not going to do that push, though. But anyway. Let f be a function from the reals to the reals such that f of x equals the arc tan of x. That's the inverse tangent function. Now, I told you to take my word for it. We said without any real proof that f prime of x equals 1 over x squared plus 1. Now, that's going to, by the real numbers, x squared is always positive. X squared plus 1 is hence always positive. The reciprocal of a positive is always positive, so that's positive, so it's greater than 0. So f prime is greater than 0, but just by common sense. For all real numbers x, again, by common sense. So f is increasing on all real numbers by common sense. Oh, that's kind of cool. That was actually kind of neat. We took something that wasn't familiar and we wound up with something that was familiar. That's pretty cool, I think. But anyway, moving on down the highway. Let's move on. Let f be a function on 0 to infinity to r such that f of x equals square root of x. Then f prime, recall, is 1 over 2 radical x, which is greater than 0 for all x in the positives. Hence, f is increasing, albeit begrudgingly. It is increasing on the positives. It increases, but at the rate at which it increases gets slower and slower. Now, we'll talk more about it's frowning. Now, I've not told you anything about concavity yet or the second derivative. The rate at which it increases slows down, but it keeps on increasing forever. Let's not get ahead of ourselves here. It frowns, but we'll talk more about that later, okay? Okay. Next, let a be less than b and let f be 2 times differentiable on the open interval ab. If f prime is greater than 0 for all x in our open interval ab, then f lies above its tangent line, all its tangent lines on AB for that matter. Any given tangent line, it'll lie above it on AB and is said to be concave up. We call it concave up if that's the case. That's the very definition of concave up. It lies above its tangent lines. The graph looks as though it's smiling. Like the right side up parabola, y equals x squared, it's smiling. Think about y equals x squared. There's other graphs that are like that too, but y equals x squared comes to mind. Now, again, let a be less than b and let f be twice differentiable on the open interval ab. If f double prime is less than 0 for all x in the open interval ab, then f lies below its tangent lines on ab and is said to be concave down by definition. That's how we define concave down. The graph looks as though it's frowning if we're looking up. So think about y equals negative 1 times the upside down standard parabola, like y equals negative 1 times x squared, for example. That would be the upside down version of the standard parabola. Upside down parabolas, they look as though they're frowning. Think about smiling and frowning. Concave down, you're frowning. Okay, whereas concave up, you're smiling. Okay, like, follow my cursor. This is smiling, whereas this is frowning. Okay. Let A be less than C less than B, and let F be twice differentiable on, well, A, comma C union C, comma B. Guys, all this is right here is the open interval AB with C taken out of it. So C, the point C itself is missing. So we're twice differentiable on this deleted open interval AB, but we're continuous on the entire open interval AB. So hence we're defined at C, and we're continuous at C, but we're not necessarily, we don't know anything about our differentiability at C. We can't say, we don't know. Let P be a positive real number such that let P be, it's going to be a teeny tiny, in general, let's just say let P be a teeny tiny positive real number. We can just go ahead and say it's teeny tiny. It doesn't always have to be, but let's just go ahead and say that it is. Let P be a teeny tiny positive real number. It does need to be positive. And let's just go ahead and say it's teeny tiny positive, such that C minus P, comma C plus P, it's small enough to where C minus P and C plus P is a subset of A comma B. So if you stay close enough to C, you're not going to transgress the open interval AB. You're not going to go outside of the open interval AB, okay? If F prime, okay, now, if F prime of C minus Q, or excuse me, if F double prime of C minus Q and F double prime of C plus Q, neither one equals 0 and have opposite signs for any Q between 0 and P, then C is said to be an inflection point of F. Okay, so C is, in other words, C is the point where you go from you switch concavity. You either go from concave up to concave down, or else you go from concave down to concave up. Now, F double prime of C may not exist at all. It might be 0, but we don't know.